This course, radon and the risks of related to radon, health risks. So my name is Marcel Broccapay. I'm actually a general contractor specializing in the measurement and installation of radon mitigation systems in the province of Quebec. I'm here today to talk to you about radon, and especially in this case here for this course, the health risks related to radon. So I've been involved with radon for the last about 12 years now. I'm a First Nation member from the community of Kitigan-Zibi and Anishinaabe in the province of Quebec. And I'm also a First Nation, or I should say one of two trainers in all of Canada that travels the country to train contractors who want to do radon mitigation work in existing buildings. So I'm just going to share my screen here, just a minute. Actually, I'm going to go get my presentation. Hang on a sec. Won't be very long. My computer is a bit slow, so please be patient. My presentation is opening up now. Okay. And I'm just going to share it. Okay. Hopefully that you can all see my presentation on the screen. And again, here, this course here, we're going to be talking about the health effects of radon and radon decay products. And I'll be explaining what that means, radon decay products, in the next upcoming slides. So this course is presented by the First Nations Adult Education School Council with the financial participation from Indigenous Services Canada. The course outline. So we're going to be talking throughout this course here about the physics of radon and radon decay products. And in order to understand the link between radon and the health risk, which essentially is lung cancer, we need to understand the physics of the radon atom and how that relates to the lung cancer at that point. So we're going to be talking about the physics and also the health effects of radon and radon decay products. Understand how the soil gases, which includes radon, infiltrates into the interior of our homes. We're going to talk about conducting measurements. How do we measure for radon? What are the protocols? And the reason we're talking about that in this course here is that this course is geared to health professionals, so nurses, those working in the health field, etc. And in most cases for First Nation communities, they would be probably the first ones or on the front line of setting up different types of radon measurement projects to test the homes in the community for radon. So that's why we're going to be talking in this course about conducting radon measurements and their protocols. We're going to talk about different measurement devices for both radon and radon decay products. And we're going to give you an overview of what needs to be done when you've found a radon problem in the home. How do we correct that? So we're going to have a radon mitigation overview at that point. So again, here to start off, we're going to talk about radon and where it comes from. So radon comes from uranium and radium that are found in the Earth's crust. So uranium and radium are metals, and like I said, they're found in the ground, typically in the Earth's crust, and we find that everywhere in the world. There's not one place in the world that we could say has zero radon. So radon does come from those two metals, And like I said, there's nowhere in the world that we could say has zero radon. Even outdoors, we would measure radon. If we were using an instrument to measure radon, we would go outside and we could even measure radon outside. Now, when the radon comes out of the ground outside, it gets diluted in the air fairly quickly. When radon infiltrates into our homes, especially nowadays, we are building our homes so airtight that when the radon infiltrates into our homes, it has a tendency of accumulating inside our home and could accumulate to concentrations that are dangerous for our health. We're going to explain how that happens in this presentation here. So typically, because it's a gas, radon is a gas, it moves up from the ground into the air above or into our homes. So the physics of radon and radon decay products. So most people have seen this image on the left here, which is an image of an atom. And if we look at it closely, we could see that we have a center part, or the nucleus, and then we have particles that are kind of flying all around the nucleus. So we can compare this to the sun and the planets moving around the sun. So in the nucleus, in this case here, in this image, we see some red marbles and some yellow marbles. We can say that the red marbles are protons and the yellow marbles are neutrons. And both of them form what we call the nucleus, or the sun, as an example. What's floating around are little green marbles. We call those electrons, and they actually form a cloud that kind of, so these things are constantly revolving around the nucleus. The protons actually have a positive charge, and the electrons are little green marbles, which are floating around the outside of the nucleus. They have a negative charge. And typically, in an atom, we have an equivalent amount of protons and electrons. So the actual charge that they have kind of balances out. We have so many protons and an equal number of electrons. So the positive and negative charges balance out. So it has overall a neutral charge, or no charge at all. In most cases, we have more neutrons than protons. So we'll see that in the next couple of slides. So the nucleus is made of positively charged protons, like we had mentioned, and neutral neutrons. And that's why we call it neutral, because they don't have a charge, and that's why we call them neutrons. The number of protons is what we call the atomic number, which identifies an element. So every element that we know has a certain specific atomic number that's attached to it, or that it's given. And the atomic number relates to the number of protons that you have in the nucleus. In the case of radon, okay, we have 86 protons in the nucleus and a certain number of neutrons. Now, in order for it to be considered a radon atom, it has to have 86 protons in the nucleus. If it does not have 86, if it has more than 86, or if it has less than 86, it's not a radon atom. It's something else. So just remember that famous number, 86. In order for it to be called a radon atom, it has to have 86 of the little red marbles, or protons, in the nucleus. The number of protons and neutrons combined is what we call the mass number, atomic mass. Let's say the weight, as an example. So both of them combined considered the mass, or the weight of the nucleus. And the number of neutrons is generally more than the number of protons. The number of electrons, like I had mentioned previously, is normally equal to the number of protons, so that the total atom has no net charge. We know that the protons have a positive charge, the electrons have a negative charge. But if they're the same number, then overall they balance out and the atom has no net charge at that point. Here's what we call the periodic table. Those that have taken chemistry over the years have probably seen something like this. And all the elements that we know of are shown in this periodic table here. So if we go to the top left here and we see a H in the first square, top left-hand corner, and we see there's a little 1, that indicates the atomic number, which also indicates the number of protons in that atom. So H stands for hydrogen. So hydrogen has 1 proton, and the atomic number is therefore 1. If we go to the top right-hand corner, we have He, which stands for helium. In that case, the helium atom has 2 protons and an atomic number of 2 in a case like that, because it has 2 protons. Now, if we go a little bit lower here in the purple square here, we see Rn, and that's the letters we use to identify radon. So like I mentioned in the previous slides, in order for it to be considered radon, it has to have 86 protons. So here we see 86. So the atomic number for radon is 86 and has 86 protons. If we go a little bit to the left here and we see this one here, it's PO, it's for polonium. Polonium is a metal. It has 84 protons. So radon has 86 and polonium has 84. And you'll see why in the next couple of slides, why I am focusing here a little bit on polonium, 84 here. So every element has a different number of protons and has a different number of atomic number at that point. Radon 222. The 222 represents the atomic mass. And the atomic mass is the combination of the number of protons and the number of neutrons. So radon 222, and it's an easy number to remember. It's our most common radon that we are aware of in our environment. And in order for it to be called a radon, it has to have 86 protons at that point, and that's the atomic number, 86. In order to get 222, the difference between 222, which is atomic mass, and 86, it means that there has to be in that atom 136 neutrons. So 86 plus 36 gives us 222. And like I said, that's the most common radon in our environment right now. There are other types, and essentially the difference between the other types of atoms is first of all, they all have 86 protons, because otherwise it would not be considered a radon, but they just simply have a different number of neutrons. So just remember radon 222, which is the atomic mass of our most common radon that we have in our environment today, 86 protons. We're going to talk about isotopes. Now, what is the definition of an isotope? So an isotope is any set of atoms with the same number of protons as another atom. So in the case of radon, if we have several different types of isotopes, they would all have the same number of protons, which would be 86. Because in order for us to call it a radon atom, they have to have 86 protons. And like I mentioned, in most cases, what would be the difference between the different atoms would be the number of neutrons. There are actually 39 known isotopes of radon, most of them very short-lived. The two most common ones is radon 220 and radon 222. Radon 222 being the most common one in our environment. Radon 222, which we also call thoron. It's an isotope of radon, and its atomic mass is 220. So the difference between the two, they're both radons, but the difference between the two is the number of neutrons. So in the case of radon 220 or thoron, it has 134 neutrons, while the radon 222, our most common one, has 136 neutrons. So there's many different types of radon, and the big difference being the number of neutrons. All of them have 86 protons. So here's an example of an isotope, and it has one proton. The red marble has a proton in the left here. The middle one has one neutron, one proton, and the one to the right has one proton and two neutrons. So this, if we were to look at the periodic table, this would be an example of a hydrogen atom because it has one proton. So it's an isotope of the hydrogen atom. So the difference between the two is the number of neutrons. So the atomic number would be 1. Atomic mass would be 1 in this case here, 2 here, and 3 here to the right. Along with talking about the physics of radon, we're going to talk about radioactivity. And that's why we spent a bit of time trying to explain the physics of radon, because that allows you to understand radioactivity and what causes radioactivity and why radon is radioactive. So we're going to talk about that. So when we talk about radioactivity, we measure radioactivity in different ways, and in Canada we use the term becquerels, pronounced becquerel. And the definition of 1 becquerel is the activity or quantity of radioactive material in which 1 nucleus decays per second. So when we talk about something that's radioactive, all we mean by that term is that what's going to happen is that the atom, and we could refer to radon here because we know that radon is radioactive. What it means is that you're going to get 1 disintegration per second. And what do we mean by disintegration? So when we talk about disintegration, I'm going to give you the analogy of popcorn, okay? And what do we do with popcorn? We take a small kernel of corn, we put it in oil, we heat up the oil, and eventually it's going to pop, and it's going to release energy. And that energy, in relation to popcorn, is sufficient to actually throw the piece of popcorn out of the cooking pot. And our final product is a piece of popcorn. So if we compare the two, we started off with a small little hard kernel of corn, and we ended up with a big piece of popcorn. Now, if we compare the two, they're not the same shape, they're not the same size, they don't taste the same, they're not the same color. They have completely changed, okay? When we talk about radon and radioactivity, that's essentially, if you want to visualize what's happening with radon and radioactivity, that's essentially what's happened. We start off with our radon atom. It's going to disintegrate, release energy in the process, and in most cases, it's that energy that's going to be dangerous for our health. So it's going to release energy, and it's going to change into something completely different. So radon is a gas, and what's going to actually happen once the disintegration process has completed, it's going to change to a metal. So you could see here, there's a drastic change when it disintegrates. So that energy that's released, that's what we call the radioactive decay, the disintegration of radon. Because once we're done, it's no longer radon anymore, it's something else, just like that kernel of corn. So becquerels, just remember, it's 1 disintegration per second. In the United States, they use a different terminology, different unit of measure to measure for radioactivity. They use picocuries per liter. So again, they measure radon in a different way. But in Canada here, we're using becquerels, and it's important for you to understand what that becquerel means. So again, 1 disintegration per second. So here we actually have a radon atom. And when we talk about radon and its disintegration, what's actually happening in the case of radon, it's actually going to eject a particle out of the core of the atom. Okay, we call that alpha decay or alpha energy. That alpha energy we call it an alpha particle. It's always composed of 2 protons and 2 neutrons all the time. It gets ejected out of the nucleus of the atom. So going back to my analogy of popcorn, so we get this energy being released, a certain portion of it gamma radiation, and a certain portion which is an actual particle that gets ejected out of the nucleus of the atom. That's an alpha particle. We call that alpha radiation. It's that particle that's actually, as I'm going to explain a little bit further, is what's the big danger for our health. So here, if that particle contains 2 protons and 2 neutrons, that means what's left over here after that particle has been ejected has only 84 protons. So what's left here after that particle gets ejected, it's no longer a radon atom because it doesn't have 86 protons anymore. It has now 84. And that's why when I was looking at the periodic table, the recent slides, I pointed out polonium, because polonium has 84 protons. So what is actually happening, once that particle gets ejected, it's going to change to polonium, which is a metal, and actually a heavy metal. So we go from a gas to a metal. It's a drastic change. But that's actually what happens when that radon atom disintegrates. When we try to find an analogy of what's happening, we can compare here to, let's say, atom A, which is oranges, and it disintegrates and changes to something else. So it changes into bananas. Call that atom B. Not the same color, not the same taste, not the same form anymore, shape. It completely changed. Now, if atom B or the bananas are also radioactive, it's going to also disintegrate and change into something else. So it actually changes into apples, atom C. And each time that occurs, radiation is released. Some kind of energy is released. And typically that energy is what's going to be dangerous for our health. So we go from a drastic change like we see here in the atomic world. When we talk about radon, it's the same thing. It's going to be a drastic change. It's going to change from a gas to a metal. That's how drastic a change is going to be. Now, we mentioned that radon comes from uranium and radium. So we're going to talk about a concept here called half-life. Now, the half-life of uranium is 4.47 billion years. Radium has a half-life of 1,620 years, and our common radon, 222, has a half-life of 3.8 days. So essentially what half-life means is that if we had a certain quantity of radon, in 3.8 days, half of it will have disintegrated. Half of it will be gone. Now I'm going to stop my presentation here just to explain something on half-life. So here, if I was to take this bottle here, okay, it's got a cap on it, sealed. And if I had 100 becquerels per cubic meter of radon in this bottle, what the half-life means, and the half-life of radon is 3.8 days. So in 3.8 days, what's going to happen is that half of this radon is going to be gone. So I'm going to be left with only half after 3.8 days. So if I start off with 100 becquerel per cubic meter, after 3.8 days, I'm going to be left with half of, or 50 becquerels per cubic meter. We let another 3.8 days go by. What we're going to see is half of what was left over is going to be gone. So we're going to be gone, half of 50 is 25. So after another 3.8 days, we're going to be left with only 25 becquerels per cubic meter. If we wait another 3.8 days, we're going to be left with half of that half. So half of 25, we're landed at 12.5. So you can see that it's not 3.8 is half is gone and another 3.8, the other half is gone. No, it's half of what's left over that's going to be gone at each time. So that's what half-life means, is that half of it will be gone. And in the second period, half of what's left over is going to be gone. I'm just going to share my screen again. So that's the concept of half-life. So here, radon 3.8 days. People ask me sometimes when I explain to them when I'm doing, radon mitigation work in a home, and I tell them it's coming from the ground underneath your concrete floor slab, and they tell me, well, how many years is it going to take for that to disappear underneath my house? And I tell them, well, in the case of radium, half-life is 1,620 years. So I doubt very much that in our lifetime, we're going to see that all gone. So again, if we look at uranium, 4.47 billion years, I don't think that's ever going to happen. Not in our lifetime anyway. So here, the half-life is the average time required for half of a sample with a large number of atoms to decay. The decay of an individual atom cannot be predicted, not time for all the atoms to decay. So I explained to you in my bottle here that if I had 100, and I think our next slide here will show it. No, sorry, I don't have it. So the decay process, 3.8 days for radon. After 3.8 days, if I had originally 100 becquerels per cubic meter of radon in that bottle, after 3.8 days, half of it will be gone. So I'm going to be left with 50 becquerels per cubic meter after 3.8 days. We let another 3.8 days go by. We don't let any more radon coming into our bottle. So what's going to be left is half of that half. So we're going to be half of 50 is 25. We're going to be after another 3.8 days. So we'll be landed about 7.6 days, 3.8 plus 3.8, 7.6. So, after 7.6, we're going to be left with 25. We let another 3.8 days go by, and we'll have half of that half. So we'll be left with 12 and a half. So that would probably be 11.4 days at that point. So again, here, just remember that it's not half of everything that's left that's going to be gone. It's half of what's remaining that's going to be gone. Here is the I guess the chain. We call it a radioactive chain. And we start off with uranium 238, and it's radioactive, so it's going to change into different metals until it gets to about radium 226, and at that point radon comes from radium. So radium is also radioactive. It's going to disintegrate and change to radon, which is a gas. So radium is a metal, changes to a gas. After 3.8 days, you get a certain percentage that's going to change into polonium 218. Polonium is also radioactive. It's also going to release an alpha particle, and it's going to change to lead-214. Lead-214 is radioactive. It's going to change to bismuth-214. Bismuth is also radioactive, so it's going to disintegrate into polonium-214. These two poloniums, by the way, their energy that's released when they disintegrate are more beta and gamma radiation. So polonium-214 is going to disintegrate and change to lead-210. And the half-life of lead-210 is 21 years. So we kind of say that it's pretty stable at that point. So we don't go on any further. So we call these, whatever comes after radon, we could call it the children of radon, the progeny of radon, radon decay products, because radon decays and creates new products, new elements. So we could say in this case here, it's the progeny of radon or radon decay products. So anything that comes after radon, which are metals, are called radon decay products. Sometimes I'll use the acronym PDR. Oh, sorry, RDP, radon decay products, sorry. So let's do a comparison here of radon and the radon decay products. The radon decay products are the poloniums and all the other metals that come after radon has disintegrated. So radon is a gas. Radon decay products are particles, metals in reality. Radon is inert. Inert means it doesn't want to mix with anything. It wants to stay in its own corner. Don't bother me kind of thing. In the case of radon decay products, they're chemically reactive. So they will react with other types of elements, etc. Radon has no static charge, static electrical charge. In the case of the RDPs, radon decay products, they have an electrical charge. And what that does is that once they're formed, because they have a charge, it's like a magnet that has a specific charge. It has a tendency of staying stuck to surfaces. So as a PDR, it may stick to your clothes, to the table, to the ceiling, to the walls, to the chairs, filing cabinet, etc. Anything it can get close to, because it has a static electrical charge, it'll stick to that surface. In the case of radon, it cannot be detected by human senses. We can't see it, we can't taste it, we can't sense it at all. It's the same for the RDPs. It's not detected by human senses. Both of them are naturally occurring. Nothing that we need to do for radon to be produced. And here, in the case of radon decay products, it's the primary source of cell damage in lungs. And I'll explain that in the next upcoming slides. We call these RDPs heavy metals. So they're actually metals, particles. When we talk about radiation, essentially in our case here, we're going to talk about three types of radiation. We're going to talk about alpha radiation, or that alpha particle, and we can consider that as an atomic cannonball. And that alpha particle is always composed of 2 protons and 2 neutrons. It's big, it's heavy, it doesn't go very far, low penetration. Beta radiation is like an atomic rifle shot. It's a small mass, moves faster, penetrates deeper. The smaller it is, the faster it goes, it's going to penetrate deeper. In the case of gamma radiation, we can consider that as an atomic laser. It has no mass, moves at the speed of light, penetrates deepest, even to the point where it'll cross through concrete. So when the radon and radon decay products disintegrate, essentially that's the 3 types of radiation that's going to be emitted, depending on the atom that's going to be disintegrating. So in certain cases, it could be a combination of alpha and gamma, or a combination of beta and gamma. Alpha radiation, alpha particle, is a particle that's released from the nucleus, like we've seen, and it always contains 2 protons, 2 neutrons. So the mass number will change by 4. So radon 222 will change to polonium 218. So you can see the difference between the two. There's 4. 222 minus 218, that's 4. And each proton and each neutron has an atomic number of 1. So in this case here, we're losing 4 every time we lose an alpha particle. And because the radon atom, which had 86, loses that alpha particle, which contains 2 protons, it changes to polonium, which now has 84 protons in a nucleus. Like I was mentioning, the alpha particle, we can consider that particle like a cannonball. It's big, it's heavy, it doesn't travel very far, but when it hits something, it does a lot of damage. And in the case when we talk about radiation causing damage in our body, especially in our lungs, we're referring to the alpha radiation or that alpha particle. So essentially, when we breathe in radon and we get that disintegration occurring inside of our lungs, the alpha particle gets released. When it disintegrates, it's going to hit living cells in our lungs. And for sure, it's going to cause damage to those living cells. And I'll explain a little bit further where the link is to lung cancer. So we have here what we call a alpha track radon measuring device. So I'm going to stop the presentation here and I'm going to show you what's inside one of these. So essentially what we have seen on the screen previously is this little device here. We call that an alpha track radon measuring device. So I'm going to open it up to show what's inside here. People always ask me, what's inside that little measuring device? So inside here, all we have is this little piece of plastic here. That's all. That's all that's in this radon measuring device here. I'll show you another model made by another company. This is also an ultra-attack detector. I'll open it up and I'll show you this one. So what do we see in this one? Little piece of plastic here, stuck to the side of the chamber. That's all it is. That's all that's in these devices here. I'll explain how that works. I'll go back to my sharing screen here. So how this works here is essentially the radon is going to infiltrate into that chamber and it's going to disintegrate inside the chamber and it's going to release an alpha particle. The RDPs that are created will also be stuck inside that chamber, and the 2 poloniums will also release alpha particles. And they're actually, those alpha particles, when they hit the plastic, they make a mark, a track on that plastic. That's why they call it an alpha track. So at the end of a 3-month period, you send it back to the lab and they will take out the plastic, put it under a microscope, count the number of pits or tracks that you have on the plastic. And at that point, they're able to tell from the number of tracks that you have what the radon level was in the room where you measure. The big question here, if that alpha particle could make a mark on a piece of plastic, imagine the damage that it's doing inside your lungs. So remember that. That alpha particle is like a cannonball. It's big, it's heavy, doesn't go very far, but when it hits something, it creates a lot of damage. And we could see it here. This is a very common type of measuring instrument that's widely used in Canada, alpha track detector. Big question, if it can make a mark, those alpha particles make a mark on a piece of plastic, imagine what's happening inside your lungs. We're going to talk about beta radiation. Now, beta radiation is a particle the size of an electron, which is released when the nucleus changes to a neutron or changes a neutron into a proton. So there's a beta particle that occurs. It could also occur where you have this alpha particle flying through the air, and it dislodges an electron from a neighboring atom at that point. So those are beta particles, very small, will travel much faster because they're very, very small, and essentially moves near the speed of light. And when it hits something, it'll go deeper. It's like an atomic rifle shot, small and goes deep. We also will have, in certain cases, the release of gamma radiation, which is pure energy. And again, whenever an alpha particle or beta particle is emitted, we also have some gamma radiation. And that no mass, moves at the speed of light, no charge. And that will even cross through concrete. So it penetrates very, very deep. If we compare the penetrating power of the three, an alpha particle could probably go through a sheet of paper, but it'll not cross through our skin. So our skin that we have on our body is a good protection against alpha particles. But when we breathe it in and that disintegration occurs inside our lungs, we don't have that skin that's protecting us at that point. So that alpha particle will hit the living cells directly at that point. The beta particle will cross through our skin, and gamma will even cross through concrete. We're going to talk here about a term that we need to understand also, to understand a little bit further what's happening, is an ion. And an ion is an atom that has either gained or lost an electron. So in certain cases, we may have an alpha particle flying through the air, dislodges because it's going through a neighboring radon atom as an example. So it dislodges an electron. That electron could end up flying into a neighboring atom, and it joins in with the other electrons that are there. So in both cases, an ion is an atom that has either gained or lost an electron. Now, why we talk about ions is because in certain cases, that creates a chemical reaction. And in certain cases, it could actually damage the DNA of certain cells. So again, that's why we're talking about what is an ion and how is it caused? How do we create an ion? So two categories of radiation. We have one that's called ionizing radiation, and the term itself explains what we're accomplishing here. Ionizing, it means that we're creating ions. And at the bottom, we have non-ionizing radiation. So ionizing radiation has enough energy to break down molecules by removing electrons from atoms, and that radiation creates specific reactions which could damage cells. And radon is a good example of ionizing radiation. Non-ionizing radiation does not remove electrons. Example is microwaves. So here, ionizing radiation, radon will cause ionizing radiation, and in certain cases you get these ions that are created, which could break down certain parts of the body or parts of cells. And there's that danger that it damages the DNA of cells. So here's an example of what I was explaining. You have this alpha particle, which contains 2 protons, 2 electrons that got released from the nucleus of a radon atom, flying through the air. It's going to hit other atoms that are in the air and could dislodge these electrons. So if a atom has lost an electron, remember we talked about the protons having a positive charge and the electrons having a negative charge, and they're balanced. They both have the same amount of protons as electrons. So net, you have no charge. But whenever you lose an electron, then you have more protons than electrons. So you're going to have an overall positive charge. Okay, here we lost 1 electron. So we have a net charge of 1, positive 1. If it was an ion that had gained an electron, then we have 1 more electron than the number of protons, and we have a negative net charge of -1 at that point. Here I have a little video. It was filmed in Health Canada's laboratory in Montreal, where they built the cloud chamber. And essentially it's an aquarium where at the base of the aquarium you have dry ice, and they have alcohol saturated with alcohol. And what that does, it creates an environment where we're going to actually be able to see those alpha particles flying through the air. So what they do is they inject radon, and then what we're going to see in the video here is the alpha particles flying through the air. So here you go. Yeah, it'll start for us. Come on. Come on. My computer is a bit slow, so sometimes it takes a bit of time before it starts up here. Okay, what I'm going to do here is I'm going to stop the presentation. I'll run the video directly here. I'll go and get the video, won't be long. Okay. I'm going to go and share that video with you. So what we're seeing here, actually, this is Isabelle Bizina. She was working with Health Canada at the time. So what you're seeing, these little white plumes in the air, are actually the alpha particles that are being released from the radon atoms. And like I was saying, it's in an environment that's saturated with alcohol, dry ice. And what I want you to notice here is that those alpha particles, they don't travel very far, probably a few centimeters, and typically will not run into a straight line. And the reason for that is that alpha particle, as it's flying through the air, it's actually hitting other atoms and being diverted. Similar to when we're playing pool. We hit the cue ball, which hits another ball, and that ball flies in one direction, hits another, flies in another direction, and you have the balls flying in every direction at that point. So that's actually what's happening here. Now, that white plume that you're seeing is actually like similar to when we're looking up into the sky and we see a plane flying overhead. That white plume of condensation that we see behind the plane, well, it's the same thing we're seeing in that aquarium here. So what they're showing here is the alpha particle hitting living cells in our lungs, and some of them may be creating cancer cells. So where radon comes from, it comes from the ground and will infiltrate into your basement, home, through any cracks, holes, openings that you have in your concrete floor. And depending on how airtight the house is, if there's not a lot of natural air infiltration coming into the basement, then it may accumulate to high levels that are dangerous for your health at that point. So any cracks, holes that you have in your concrete floor, concrete foundation, radon could infiltrate into your basement at that point. So again, here, these plumes are what's created like the back of a plane, that plume. That's what we're seeing here, is the condensation. Radon infiltrating into the basement. So things to need to do to try to minimize that infiltration into your basement. We could seal all the cracks, openings, or we can install a system will capture the radon underneath the concrete floor and shoot it outside before it has a chance to get into the basement of your home. I'm going to stop this one. I'm going to go back to my presentation. So that was the video that we were showing you. So we're going to talk about the health effects now of radon and the radon decay products. And again, the major health risk is lung cancer. So radon and radon decay products are known human carcinogens. And otherwise, they're known to cause cancer in humans. Here we mentioned that the effective total dose delivered is about 97% from the RDPs and about 3% from radon. So in other words, the big risk of getting lung cancer comes from the radon decay products, the RDPs, rather than radon itself. Now, to explain this, when we talk about radon, which is a gas, we breathe it in, we breathe it out. We breathe it in, we breathe it out. We breathe it in, we breathe it out. For that disintegration to occur and that release of the alpha particle to occur exactly at the moment that that radon is landed in our lungs, the chance is pretty small. In the case of the RDP, the radon decay products, because they're metals, when we breathe them in, they stay stuck in our mucus lining in our lungs. And when they disintegrate, well, they're right there inside our lungs. So for sure, that alpha particle is going to hit some living cells in our lungs. So we say the risk of getting lung cancer, if we compare radon to the radon decay products, probably 97% of the risk is coming from the RDPs, the radon decay products, and only about 3% from radon. You might say, well, why are we not talking about RDPs instead of radon? Why should we not be talking about measuring radon decay products versus measuring radon? Well, the instrument to measure for RDPs is very expensive, probably talking about $10,000 plus. The instrument to measure for radon, we've seen it's just a little piece of plastic. That's probably about $20 to $30. We know that if you have radon, you're also going to have RDPs. They go hand in hand. So if you measure for radon, you can estimate what the RDPs are going to be. So that's why we're talking about radon and measuring for radon rather than RDPs. So radon is actually a known, proven carcinogen, human carcinogen. It's a known fact that radon and radon decay products will cause cancer in humans, just like arsenic, asbestos, benzene, dioxin, mustard gas, radionuclides, radium, etc. So just remember, it's proven through a lot of different studies, and almost every country in the world at one time or another has undergone a study for a relationship between radon and cancer. In most cases, the numbers, the percentage may change from one country to the next. Saying one country maybe will say 10% of our lung cancers can be related to radon. Another country may say 12%, of the lung cancers can be related to radon. In Canada, it's estimated at about 16%. With the study that have been undertaken, 16% of the lung cancers can be related to radon. The numbers may change from one country to the next, but they all say one thing, that there's a link between radon and lung cancers. They all say that. Percentages may change, but they all say one thing in common: radon is a human carcinogen. Tobacco in Canada, it's still the #1 cause for lung cancer. Radon and the RDPs, radon decay products, it's the second leading cause of lung cancer in Canada after tobacco for smokers. Okay. Radon is the #1 cause for lung cancer in non-smokers, considered as an environmental risk. So for smokers, tobacco is still #1 for cause of lung cancer, and radon #2. For non-smokers, it's #1. So if you know somebody that never smoked in their life and got lung cancer, there's a good chance it came from radon. So it's estimated that about 1 person in 7, or 16% of people with lung cancer, that could be related directly to radon. That represents a number of about 3,200 lung cancer deaths per year in Canada. This chart here, the 5-year survival rate ratio. So if we look at the bottom white bar, which represent prostate cancer, you have a person that got prostate cancer has about a 95% chance of living past 5 years. 5-year relative survival rate. So if we look at the blue bar, that represents breast cancer in women, they have 87% chance of living past 5 years after they've been diagnosed with breast cancer. In the case of lung cancer, the top one, the red one, once they've diagnosed lung cancer, you have about a 15% chance of living past 5 years after they've detected the cancer. So your 5-year survival ratio is very small. So if there's one cancer you don't want to get, it's lung cancer. Your survival rate is very, very small. So something to take into consideration at that point. So here again, mechanism for lung cancer, you're breathing in the radon, RDPs, that disintegrates in your lungs, and that alpha particle gets released. And for sure, it's going to hit living cells inside your lung. And it's going to damage. We've seen that if it can damage a piece of plastic, it'll do damage to living cells. Now, in probably 99.999% of the time, it kills this living cell in your lungs. Now, cells that die in our body, it's not the end of the world, because we have new cells that are going to regenerate themselves to replace that cell that died. That's a natural cycle in our body. Good example of this is blood. Let's say we go to the Red Cross and we give blood, a liter of blood. If our body would, our red and white blood cells would not regenerate themselves to replace those cells that are gone, we would probably give blood 3 times and would be dead. Now we know that doesn't happen. So we know that whatever we gave in terms of blood will be replaced by the red blood cells that are going to regenerate themselves to replace the cells that are gone. So it's not the end of the world if the cell dies. The next thing that could happen is that it hits a living cell, that alpha particle hits a living cell, and it doesn't hit the cell in a critical spot. So in a case like that, the cell could repair itself. So just like our body, we cut our hand or cut our arm, our body is going to repair itself at that point. So living cells can do that too. So if that's the case, not the end of the world. The big danger here is if the alpha particle hits a living cell just in the wrong spot. And here, for simplicity, I'm going to say in the brain of the cell. Now, when that alpha particle hits that cell just in the wrong spot, it could damage the DNA of that cell. And the big danger here is that if the cell survives, then it has damaged DNA. So remember what DNA is we received a certain amount of DNA from our father, we received an amount from our mother, they combined together, and that's why today we have an example: brown hair, brown eyes, 2 arms, 10 fingers, 2 legs, etc. It makes what we are today, okay? That mixture of DNA is what makes us who we are today. When the DNA is damaged, and that cell that survived that damage now has damaged DNA, so when it's going to duplicate itself, reproduce itself to replace a cell that has died or is gone, because the DNA is damaged, the new cell produced will have sustained mutation. So we end up with a cell that may have 4 eyes, 4 arms, 1 leg kind of deal. So that's what we call a mutated cell, because the DNA was damaged. Now, a damaged mutated cell, a mutated cell is what we call, is a definition for a cancer cell. So that mutated cell is now considered a cancer cell. Now, that cancer cell, and we've kind of lived that experience with the COVID virus over the last 2 years, where the virus has mutated into a new, version. And sometimes that new version or mutated virus is either, could be more dangerous to our health, maybe transferred from one body to one other more easily, etc. So in certain cases, that virus becomes more dangerous than the original one. So in our body, with this cell here that has mutated because of damaged DNA, in certain cases could become stronger than the normal cells. And that could provoke the growth of the cancer at that point. So you could get masses and tumors forming, because in certain cases, it'll replicate itself, duplicate itself at an alarming rate, or just be simply stronger and develop into masses and tumors at that point. Remember one thing, our body, we all have cancer cells in our body. They don't all develop into cancer. Like, we have an immune system that in most cases will either quarantine those cells because they know it's a living cell, but it's not normal, so they quarantine it. In certain cases, you may have genes that will destroy it. So depending on your immune system, in certain people it may develop and others not. So in certain cases, sometimes we have, your genes will quarantine it, and it'll stay that way for years and years and years, until you get older, you're into your 50s, 60s, and 70s, where your immune system starts to get weaker. You start having problems with high blood pressure, diabetes, cholesterol, other organ issues. So at that point, your immune system is getting weaker. And that's where, in certain cases, where these cancer cells, which have been kind of dormant all these years, now have a chance to reproduce. And in certain cases, it may be something that you had an event occur in your body when you were in the 20s, and the cancer develops in your 50s, 60s, or 70s. So again, in this case here, how it creates havoc in our bodies, how it creates that mutated cancer cell, is this alpha particle, which has hit a living cell, damaged the DNA, the cell survived, and the next time it duplicated itself to replace a dying or missing cell, that's where you get that mutated cell occurring. The lung cancer is considered monoclonal. In other words, all it takes is one event, just one time where that alpha particle hit a living cell, didn't kill it, the cell survived, but the DNA got damaged. You might be in your 20s, your immune system is putting it in quarantine, and 30 years later, when your immune system is starting to get weakened, then it develops at that point. So that's essentially for lung cancer, that's one of the things to consider. Now you're going to ask me, well, how did they notice? How can they tell what this health risk is? So there are many different types of studies that have been undertaken, like I said, by a lot of different countries. And the best types of studies to determine health risk are either cohort studies or case control studies. A cohort study essentially, and a lot of them were done with minors, where an individual is exposed to something that causes cancer, and you follow him through this entire life to see if he gets cancer in 20, 30 years from now. That's a cohort study. A case control is somebody that has cancer, and you back up in his life to see where he could have gotten that cancer from. So that's a case control. Ecological, those studies are not really recommended for risk assessment. It's like what you're doing is you're studying all the people in a certain town to see if they develop cancer. It doesn't tell you anything about a specific individual. So those types of studies are not really recommended for risk assessment, because you can't really put a finger on a specific individual. Cohort case controls is you're dealing with individuals at that point, and that's where you know there's a direct link between the lung cancer and the individual self who got exposed. So every country has undergone different types of studies. The percentages will probably differ from one country to the next. Some of them may say, well, 10% of the lung cancers can be related to radon. Another country may say 16%, another one may be 12. But essentially, they all say the same thing. No one says different, is that there's a link to lung cancer from radon. Health Canada has an actionable level set at 200 becquerels per cubic meter. So, and this level here, they deem it as an acceptable level. It is not a safe level. In other words, what I'm saying here, if your levels are at 190 and the actionable level is 200, it doesn't mean that at 190 you're safe. You're not going to get cancer. What it means is that they've determined that level to be acceptable. In other words, the number of deaths that occur in Canada every year is acceptable at the level of 200. That's all it means. It doesn't mean that it's a safe level. There's actually no safe level when it comes to radon. When remedial action is taken to lower levels in a home that have excess levels above 200, Typically, the techniques used nowadays can reduce those levels to way below 100, below 75. Now, I'm going to do a little exercise with you guys here. So let's say you have an office that's 10 feet by 15 feet with ceilings that are 8 feet high. So I'm going to convert that to metric, and I'm going to round the numbers here, and I'm going to say that office that you're working in every day, 3 meters by 4 meters by 2.4 meters high. I'm going to multiply that together. So 3 times 4 times 2.4. In that room, we have 28.8 cubic meters of air. So I measured the 10 feet by 15 by 8 feet high ceiling. What I did is I converted to meters instead of doing it in feet. So rounding it off, 3 meters times 4 meters times 2.4 meters high, we get 28.8 cubic meters of air. And why am I using cubic meter? Is because the actual level set by Health Canada is 200 becquerels per cubic meter. So I need to calculate how many cubic meters are in that room. So I'm saying here, once I multiply the 3 times 4 times 2.5, 28.8 cubic meters. And I'm going to multiply, let's say you measured your office and you had 200 becquerels per cubic meter. So I'm going to multiply that 28.8 times 200. And I get a number of 5,760. Remember what a becquerel is. It's 1 disintegration per second. So when I multiply the 28.8 times 200, what I'm getting here is 5,760 disintegrations from the radon, those alpha particles flying through the air. 5,760 disintegrations per second in that room. Now, if I want to find out how many disintegrations in a minute, I'm going to multiply that by 60. So multiplying that by 60, I get a number of 345,600 disintegrations in your office every minute. I'm going to repeat that. 345,600 disintegrations, those alpha particles flying through the air, every minute. Are you susceptible to breathing in some of those, that radon and those disintegration? Yes, definitely. You will be breathing in those radons and you will be getting those disintegrations occurring in your lungs. That's a lot of disintegrations in that room. That's happening all around you. Like we see it in that cloud chamber, that's occurring all around you right now. I want you to imagine what you're seeing in that aquarium, that cloud chamber. If you were able to visualize that, that would be occurring all around you right now. At what rate? 345,600 of those disintegrations occurring all around you in the room every minute. Back in 2007 or prior to 2007, the actionable level that was set by Health Canada was 800 becquerels per cubic meter. They reduced that to 200 back in 2007, in June of 2007. So at 800, what were the chances of somebody getting lung cancer? For a smoker, 30%, or one smoker in 3 had the risk of getting lung cancer. For non-smoker, about 5%, 1 in 20. When they lowered down to 200, at that point, 17%. Smokers had a 17% chance of getting lung cancer at 200, and for non-smoker, about 2%. So at 800, back before 2007, There was no action required to lower the levels if your levels were at 800 or less. So again, 1 becquerel per cubic meter, 1 disintegration per second in a cubic meter of air. That's what that means. Becquerels per cubic meter. The US uses a different one. They use picocurie per liter. So to convert between the two, 37 becquerels per cubic meter is equal to 1 picocurie per liter. The actionable level in the States, in the US, is 4 picocurie per liter. So if we multiply that by 37, that gives us about 148. So we round that off to 150. So the American actionable level is equivalent to our 150 becquerels per cubic meter here in Canada. Back in the 90s, the people in the States, they did not understand very well, what does that 4 picocuries per liter mean? A lot of times people would measure for radon in their homes and they'd find the levels maybe at 6. And they'd say, well, my level is at 6, just a little bit above 4, not that bad. Somebody else would measure 8 and it'd probably say the same thing. My levels are at 8, just above 4, not that bad. Here in Canada, same thing. You know, we say somebody's at 280 or 300. Okay, we're just above 200. Not that bad, not the end of the world. So back in the 90s, the Environmental Protection Agency, the EPA in the States, wanted to find something that the people could compare more easily to. So they took cigarette smoking. And what they determined is that 370 becquerels per cubic meter here in Canada is equivalent to smoking a pack of cigarettes a day. So what does that mean about our 200? So that's about half of 370. So that means that 200, if your levels are 200, that's like smoking half a pack of cigarettes a day. Now, to somebody that never smoked in their lives, they'll probably say that 200 is I can't accept that. I want something a lot lower. To a smoker, oh, I already smoke a pack of cigarettes a day, so another half a pack, not the end of the world. So it becomes a personal choice at that point. Is 200 acceptable, or would you prefer to have something much lower? So again, just to give you an idea about those numbers that we're throwing out there. So what affects radon entry and their concentrations in our home? And like I said previously, back in the 80s, you know, there's a lot of there was natural air infiltration into our homes. Didn't really have a radon problem back then. Nowadays, we're building our homes so airtight that there's very, very little natural air infiltration that makes its way, you know, underneath our exterior doors, around our exterior doors, windows, etc. So it's landed to the point where our homes are so airtight that we have to mechanically bring in fresh air from the outside to get sufficient fresh air at that point, because it doesn't come in naturally anymore through cracks around doors, windows, etc. Nowadays, we see that when there's a pollutant that gets into our homes, that has a chance of staying there for longer periods of time. And it's landed to the point where the most polluted air we're going to be breathing is inside our own homes. What actually influences those radon levels in our home? So again, here we could talk about the local geology. Is there a lot of rock in your area that contains, you know, uranium and radium? How about the soil underneath the house? Does it contain a lot of radium? What's the moisture content? Temperature differences, permeability? Do you have sand, gravel, rock underneath your home? More chance of having a radon problem with that kind of soil versus clay, as an example. Clay is very dense. It'll prevent the radon from coming through the clay itself. Water table, fluctuation of a water table. So if your water table rises in the spring, has a tendency pushing more radon into your home. Barometric pressures. So from one day to the next, that pressure outside your house could cause more radon to make its way inside your home. The wind, the direction, the speed, the rain. If it rains very hard, the water saturates the top of the soil, creates a pressure on the soil, which pushes more radon in your home. Different season, temperature differences, temperature inversion between wintertime when you're heating, summertime when you're cooling. Snow cover, frozen soil in the wintertime. The radon can't make its way out of the ground. The ground is frozen. So where does it come out? Where it's not frozen, which is typically around your house. Heating systems, pressure differences between the house and the soil. If you have a furnace, you may have certain zones in your basement where you don't have a balance system, where you may have a problem in one corner of the basement and not the other corner. Ventilation rate, how much fresh air is getting into your house through, cracks in the round doors, exterior doors, windows, etc. Your water source. If you have a well, your water's coming maybe from 100 to 200 feet underneath the ground. So we know the radon comes from the ground. So it may actually be carried into your home with the well water. You may have certain building materials that are made with stones that contain a lot of radium. Occupants opening windows, if you open up windows in the basement, you're going to be bringing a lot of fresh air from the outside, which is going to dilute the levels in the basement. So again, depending the occupants, what they're doing, they may be either creating a problem or not, or fixing a problem manually. If you're using a fireplace or wood stove, those are acting as exhaust fans, essentially. You're taking air from the basement and you're shooting it up the chimney. So you may be depressurizing your basement, causing radon to infiltrate into your home. Same thing with exhaust fans. So there's a lot of factors that influence just how much radon is getting into your home, as you can see. Now, here's a little picture. We can see that the radon can infiltrate into your home in a lot of different areas. Essentially, any cracks that you have in the foundation, the floor, even water, could allow radon to get into your home at that point. Now, how radon infiltrates into your home, we can kind of compare that to a hot air balloon. What do we do with a hot air balloon? As we heat up the air that's inside the hot air balloon, the hot air being lighter than the cold air will go to the top of the hot air balloon. And that's actually what's going to create a buoyancy force, which is going to cause the hot air balloon to rise into the air. Now, when we heat our homes in the wintertime and all the windows and doors are closed, the same effect happens. All our mass of heated warm air will slowly rise to our ceilings, and our ceilings are never perfectly sealed. There's always some small holes around lights, corners of walls, around windows. Electricians made holes to pass their wires. Plumbers made holes to pass their pipes, trap door, etc. So you can imagine this mass of heated warm air that's slowly rising to your ceiling, and eventually will find a place to escape outdoor, typically through your attic. During the heating season, this movement of this heated mass of warm air that's slowly rising to your ceiling, it's continuously in motion rising to your ceiling. And what it actually does, it causes your house to become like a large vacuum cleaner, creating a suction in the lowest level of your home. The term we use to describe that is stack effect. So it's this stack effect that's caused by this rising warm air continuously moving upwards. That's causing your house to become like a large vacuum cleaner. It's this stack effect that's creating this suction in the lowest level of your home. And it's this suction that's going to suck the radon through any cracks, openings, holes that you have in your concrete floor. One of the prime locations for the radon to get into your home is a crack that forms between the foundation wall and the edge of your concrete floor in the basement. And the reason for that is originally when they poured your concrete floor in the basement and it started to dry, there was shrinkage that occurred. So in that case, we end up with a crack between the foundation wall and the edge of your concrete floor. That crack, in the majority of cases, is not that wide. There may be a 1/16 or 1/8 of an inch wide. But at 1/16 of an inch, it would mean that every 16 inches, that crack would represent an opening that's about 1 square inch. And when we measure the whole perimeter of your basement, that crack could represent a hole that's about 1 foot by 1 foot where the radon can infiltrate into your basement at that point. If you have a sump in the basement where you could put a sump pump if ever you got water in the basement and you didn't have a sealed cover on it, then that's simply another location where the radon can get into your home. Sometimes we see just a hole in the concrete floor with a small pit dug in the sand, and if the water was to come up, then you put a sump pump down there. Well, that's a nice big hole where the radon can infiltrate into your home. If you have teleposts, metal posts that are supporting your main beam from your main floor, those posts are made out of metal and they're hollow, and they'll cross through the concrete floor. So a lot of times to the center of those posts, radon can infiltrate into your basement. If you have a basement bathroom and you have either a bathtub or shower in that basement bathroom, the plumber typically will have a nice big hole, probably about 16 inches by 16 inches underneath the shower, the bathtub, to allow him to install the P-trap underneath the shower or bathtub. When he's done his work, normally that's not sealed back up. So now you have another big hole where the radon can infiltrate into the basement of your home. If you have any cracks in your concrete floor slab, it's simply another area where the radon can get sucked into the basement of your home with this stack effect. So there's actually a lot of places where the radon can infiltrate into your home. Now, to understand when we're going to be talking about a radon mitigation system or an active subslab depressurization system, we need to understand the basic principle of what we want to accomplish here. And one of the things you need to understand is air will always move from a high pressure to a low pressure. Okay, if you have any air movement, it'll always go from a high pressure to a low pressure and not vice versa. So that's the first thing you need to understand. On the left here, okay, we see our stack effect, our vacuum cleaner here, stack effect, that's creating a suction in the lowest level of our home. Now, whenever we use the term suction, whenever we use the term negative pressure, what we mean is that we're doing a comparison with pressures from two zones. And the lower pressure out of two zones is what we call the suction side pressure or the negative pressure side. So when we say that our stack effect is creating a suction in the lowest level of our home, what we actually mean is that we're going to lower the pressure in the basement of the home. And at that point, the pressure in the ground will be higher than what it is in the basement. And it's that pressure in the soil that's actually going to push the radon inside your home. On the right-hand side, we see that there's a radon mitigation system installed. So essentially, we have a pipe that crosses through the concrete floor in the basement. We have a pipe here that goes up to the attic. We have a radon fan installed in the attic, and we're going to discharge the gas up through the roof. Now, what we want to accomplish with that radon fan is we want to be able to create a suction underneath your concrete floor that's going to be stronger than the suction you have inside the home and the basement with this stack effect. So it's like a tug of war. The one that's going to pull the hardest is the one that's going to win the battle. So if we're able to create a stronger suction underneath your concrete floor, then we're going to prevent the radon from getting into the basement at that point. Now, remember what I said about the word suction. What we really mean here is that we're going to lower the pressure underneath the concrete floor. And in this case here, the pressure in the basement will now actually be higher than what it is underneath the concrete floor. So that pressure is actually going to prevent the radon from getting into the basement. So that's what we call the basic principle of what we call an active subsoil depressurization system. It's one of the techniques that's the most efficient at preventing radon from getting into your home at that point. So we're playing with pressures here. So we're playing with the pressures in the basement versus the pressure below the concrete floor. So that's essentially what we're doing with an active soil depressurization system. So again, a little review, remembering that radon comes from uranium and radium, which are metals, and they're found in the Earth's crust. And radon is also radioactive. It's going to disintegrate, produce radon, which is a gas. And because it's a gas, it's able to travel through the soil up to the surface. So essentially, that's what's happening with radon. Now, here I mentioned where radon gets into your basement. It's caused by this stack effect. So a lot of times you get a crack forming between the foundation wall and the edge of your concrete floor. So this is one of the primary locations for the radon to get into the basement of your home. And it gets sucked in with the stack effect. Now in new construction, for those that may have taken the course back in May, during the construction, what we want to do is try to prevent or use techniques to try to prevent the radon from getting up that crack. So you have a membrane here, a plastic membrane. Now, if you're able to seal that up against the foundation wall or the top of your footing here, then that would create a barrier and your gas would not be able to get up into that crack here. So in the course we gave in May on radon, we were concentrating on new constructions, and that's one of the areas that we need to put into application so that radon doesn't come up that crack. If you have a sump with a sump pump and you don't have a seal cover on it, then again, it's simply a nice big hole for the radon to get into your basement. Here we see a good example underneath a bathtub where you see a big hole through the concrete floor. And that's to allow the plumber to go put the P-trap underneath the bathtub or shower. And a lot of times that's not sealed once he's done his work. So again, another nice big hole for the radon to get into your basement. Here we have a pipe in preparation for a future bathtub shower. So essentially it's a big hole and it's not sealed. So if it's in this mode here, then it's simply another nice big hole for the radon to get into your basement. If you have a home with a crawl space, in other words, no concrete floor in the basement, the concrete floor actually acts as a barrier in itself, prevents a good portion of the radon from getting into your basement. But when you have a crawl space where it's direct gravel, sand, whatever, then it's easy for the radon to just come out of the ground into the home at that point. You need to put in a good sealed membrane over the floor to try to prevent that radon from getting into the home. But what are the driving forces and the air pressure differences is what I explained in the previous slides with that stack effect. So we're playing with pressures, the pressure in the basement, pressure underneath the concrete floor, air pressure differences. That's one of the main driving forces of why radon gets into your home. We're going to talk about diffusion, emanation, and well water, which are other ways radon can get into your home. So again, remember in a home that we heat, we have a stack effect, which creates a suction in the lowest level of your home. We could say that it's actually lowering the pressure in the basement of your home, and the pressure in the soil is actually becoming higher at that point. It's pushing the radon into your home. So air pressure differences. That represents about probably 90 to 90% of your infiltration of radon into your home. That's the major driving force. Diffusion. Diffusion actually, because concrete is porous, it's radon that goes right through the concrete itself. Now, it'll always diffuse from a high concentration to a low concentration. So just to give you an idea of what the concentrations are in the basement versus underneath the concrete floor slab, if you measure that example 300 becquerels per cubic meter in the basement of your home, typically we're looking at probably about a 1 to 100 differential ratio between in the basement and underneath your concrete floor slab. So at 300 in the basement, most likely you're looking at something about 30,000 becquerels per cubic meter underneath your concrete floor. So it'll go from the high concentration to the low concentration, which is inside your basement. So with that being said, for those that do work sometimes in basements of homes and they're breaking the concrete floor, just remember that when you're breaking a floor and you might be on your hands and knees picking up pieces of concrete, you may be breathing in levels of radon that may be in the thousands, or like 20, 30, 40,000 becquerels per cubic meter. So in case like that, good to wear a good quality filter P100 to do your work in breaking the concrete at that point. Emanation. Emanation essentially is coming right off the surface of a material. So here we could be talking about granite countertops. You may have fireplaces with field stones. You may have something in the concrete itself where the stone used contains a lot of radium, etc. So this is something, usually these materials do not create a major radon issue in the home. But if you're measuring for radon and you put your measuring instrument directly on top of a granite countertop, as an example, or on top of the mantle of a fireplace, that may bias your readings. So you may actually get higher readings than normal. So an example here, we have one home, 312. It was sitting on a granite countertop, and you did another test and it was low. So the granite countertop as such, did not, I would say, contribute a lot to the levels of the home. In this case here, maybe only 18 becquerels per cubic meter. But when your instrument is sitting directly on the granite countertop or the mantle of the fireplace, it's getting it real close at that point. So it'll bias your readings. We also have well water. So if you have a well and there's a lot of, you're in a radon prone area, you may get a lot of radon coming into your home when you're taking baths, showers, using the dishwasher, washing machine. Anytime you heat up water, you agitate water, you will outgas a lot of radon if there's a lot of radon in your water. So the appliances that outgas the most essentially is your dishwasher, because you're using a lot of very hot water. And secondly, you're agitating that water inside the machine. Washing machine, washing the clothes, same thing. You're using hot water and you're agitating that water. So these are two appliances that outgas a lot, usually. Now, in a home, if we were to, and here we're going to relate to a home that's got electric baseboard heating as an example. So typically, if we measure on the different levels of the home, let's say we were to measure 400 becquerels per cubic meter in the basement. Typically, what we would see on the first floor would probably be about 60% of what we measured on the lower floor. So you'd measure probably 240 on the first floor, and if we went up another level, probably about 60% of what you measured on the level just below. So again, probably about 150 on the top floor. So people often ask me, we typically see highest levels in the basement. Is it because radon is heavier than air? The answer to that is yes, radon is heavier than air, but that's not the real reason we're finding higher levels in the basement. The real reason is because you're closer to the source, and the source is the ground underneath your house. So the closer you are to the source, the higher levels you're going to see. The only time that would change is if you measured on a 3/4 and you've seen higher levels on the upper floor where typically the main bathroom would be. You could have radon in water. That's usually an indicator that you have radon in water, because when you're taking baths and showers, radon is outgassing and adding into the level of the radon that's in that level. So if you had, in this case here, see with a picture, 150, And if you had a lot of radon in your water, maybe every time you took a bath or shower, you generated another 100 becquerels per cubic meter. So that 100 could add on to that 150, and it could be 250 on the second floor. So once we see higher level on a specific higher floor, that's usually an indicator that we have radon in water, if you have a well. So here's some studies that were done, and it pretty well shows that in the basement is where we always see the highest levels. Now, again, this course was developed for those working in health, because typically they're the ones that are going to be doing the measurements in community houses, van houses, etc. So we're going to talk a little bit about how to conduct those measurements, protocols, and guidance. So Health Canada actually did a radon survey back in 2012. I think it was 14,000 homes in every province of Canada. And these are the results they got. So in New Brunswick, as an example, they estimated that 25%, well, actually 25% of the homes they measured showed levels above 200. Manitoba, 24%, Yukon, 20%, etc. In Quebec, it was about 10%. And overall, it was about 7% of the homes that had levels greater than 200. Now, we did our own radon project, measurement project back in 2008, 2009. And Kitigan-Zibi is actually not in a radon prone area. So we did measurements in 500 homes, and about 42% of the homes actually showed levels above 200. So again, we're in the province of Quebec. Typically, if we would just use that number, we would typically say it should have been 10% of the home, but it was actually around 42%. So this is a survey of a certain amount of homes, not all the homes in Canada. So it gives us an idea, but sometimes when you do, especially community-wide radon survey, we realize that those numbers may be a bit low than what we're actually seeing out in the field. When you're measuring, especially in a municipal style or a city or something like that, you'll notice that from one house to the next, sometimes you get some pretty wide distributions. So here, if you look, anytime there's a star, it actually means that it's above 1,000. And sometimes just right the house next door has levels less than 150. So we see that a lot in the distribution here, where right next door, the neighbor has levels less than 150, and the neighboring house has levels over 1,000. So that's common to see that. So it's not because you have a radon problem that automatically your neighbor has a radon problem, or vice versa. Really, you have to measure to find out if you have a radon problem or not. Guidelines for radon measurements in homes. You have this guide here that you can actually download from Health Canada. If you went into Google, guide for radon measurements in residential dwellings, Health Canada, you can actually download this free. Health Canada recommends long-term measurements, 3 months or more, essentially 3 months to 12 months, up to a year. That's what they recommend. They also have a guide for public buildings. So if you're thinking of measuring schools, health centers, etc., they have this guide here that you can use. And again, recommended long-term measurements, 3 months up to a year. Now they say minimum 3 months up to 12 months, with 12 months being optimal. So you're measuring through every season at that point. For durations less than 12 months, they say to include maybe a mix of seasons. In other words, maybe fall and winter, winter and spring. That would be ideal. And at least ideal time of the year to measure it in the summertime. A lot of people open up their windows. And at that point, you're going to bias your measurements if the windows are open. In certain rare cases, a more rapid indication is required. And so what they're saying here, typically a short-term test, which normally will be from 2 to 7 days, and testing less than 2 days is never acceptable. And a short-term test should not be used to recommend taking corrective action or remedial action. They also strongly recommend that a short-term test be confirmed with a long-term test, not to rely only on a short-term test for radon mitigation. All measurements should be made in the normal occupancy area of the lowest level of the house, typically the basement. And what do they mean by normal occupancy? Is any occupied area by an individual for more than 4 hours per day. Good locations, dens, bedrooms, and bedrooms is a good location because for sure the people will be spending more than 4 hours a day in that room. Family rooms, living rooms, playrooms, and again, if there's children in the house, bedroom or playroom preferred, because that's where they're going to be spending a lot of their time. Places that we should not measure: bathrooms, closets, hallways, crawl spaces, laundry rooms, near sump for sump pumps, because a lot of times we don't spend more than 4 hours a day in those locations, and in certain cases the level of humidity may affect certain test devices. So those are locations that we don't want to. Kitchen is another location, again, because of high humidity, and the exhaust fan may alter the radon concentrations during the process there. So here we have a little plan. We could see good locations, bad locations. So again, bedroom, yes; playroom, yes; closet, no; laundry room, no; furnace room, no; kitchen, no; garage, no; living room, yes; bathroom, no; bath, no; hallway, no; bedroom, yes. So these are out of view, very visual for good locations and not so good locations. Where do we place our devices? They recommend placing it by an interior wall, 40 centimeters or 16 inches from an interior wall, 50 centimeters or 20 inches from an exterior wall, at least 1 meter from a window or outside door, at least 50 centimeters or 20 inches from the ceiling, 0.8 to 4 meters or 3 to 6.5 feet above the floor, and 20 centimeters, 8 inches from any other object. So we don't want you putting a device in between books in a bookcase, as an example. You want some free-flowing air around your instrument. Now going back here to 3 to 6.5 feet above the floor, that's what we call the breathing zone. So if you're standing up, you're breathing air between 5 to 6 feet. If you're sitting down, probably be 4.5 feet. If you're lying down, maybe around 3 feet. So that's what we call the breathing zone. So I always tell people, from the height of your knees to the top of your head, in that area, that gives a good indicator. Other things to watch for: you don't want to put the instrument in direct air currents, which may be caused by a heating system, furnace, ventilation system, air conditioning system, near doors, windows, over radiators, near fireplaces, in the direct sunlight, and not near electrically powered equipment or appliances such as televisions, stereos, speakers, computer equipment, etc. Because some of those will create electronic interference with your devices. So here is just simply another graphic showing the dimensions we've seen previously. And again, here, like we had mentioned, try to stay away from granite countertops, pool tables, because some of them have slate tops. and that slate, which is actually a stone, may contain radium. So again, those are things that you want to try to avoid. Or other stone surfaces or materials. Again, here could be a mantle of a fireplace out of natural stone. So there's possibilities of radon emanation in those cases. Retesting should always be reconsidered whenever you're doing any major renovations, because those renovations may actually cause a radon problem in your home. So if you're building a basement bedroom, a basement family room, etc., would be good to retest once you're done, because possibly those renovations may create problems for you. So again, long-term measurements, Health Canada recommends taking corrective action if the levels are greater than 200 becquerels per cubic meter. So in that case, for long-term tests here. If it's under, then no remediation is recommended. What is the time frame to remediate? If your levels are between 200 and 600, they say you should take corrective action within the next 2 years. If your level is above 600, you should take corrective action in the next year. If you're below 200, no action required. With the radon measurement devices, there are a lot of different types. You have alpha track detectors, electric ion chambers, digital detectors, activated charcoal absorption devices, charcoal liquid scintillation devices, electric ion chamber devices, again, different types here, continuous radon monitors, etc., etc. We're going to concentrate on those models that you would probably be using here in Canada if you want to measure in your community, are the long-term devices. And the most common ones that are used nowadays are the alpha track devices. And we've seen these previously. What's in these devices is simply a piece of plastic. So you set it out for 3 months. At the end of 3 months, you put it in a Ziploc bag, send it to the laboratory. They'll take out the little plastic film that's inside, put it under a microscope, and with the number of pits that these see on the plastic, they're able to tell what the radon levels are in the room where you measure, and they'll send you a report on that. Very common device used in Canada. So again, here's what you would see under the microscope. We have digital detectors also. All kind of new devices are coming out every year. These devices, essentially, you can get the readings directly on the machine itself or through your phone, through an app, your smartphones. And they're okay for homeowners. As a professional doing radon measurement, we can't use these devices because we can't analyze the data from hour to hour. It'll give you what the average radon levels are over the past week, over the past month, etc. But as a specialist, we need to know if there's something funny that happened over the last 7 days. Is there something that occurred that may have peaked your system? So we have to be able to analyze that data. And these devices don't allow us to do that. So we have to use commercial grade devices. But for homeowners, it's very useful for them because they see the average radon levels from day to day, which is all they want. So it's very nice. They love these devices. A lot of them use it in every room in the home. And these devices can go from somewhere between $150 to $250. So they're very affordable. And more we're seeing a lot of homeowners using these type of devices there in their homes. And in the end here, we're going to talk about installation, radon mitigation installation systems. And essentially the go-to type of system is active subslab depressurization system. So here, essentially, we had seen one previous slide where the radon fan was installed in the attic. This one here, the radon fan is installed in the basement, and we have a discharge pipe going out to the foundation wall or in the ribbon joist just above the foundation wall. So this type of installation is also accepted by Health Canada. So here in Health Canada documentation, we can see the two types of installations that are acceptable. Radon fan on the left installed in the basement with a sidewall discharge, and the other one with the radon fan installed in the attic and discharging through the roof. Here's some pictures of some of our installations, just to give you an idea. And that pretty well ends our presentation here. This slide here has my contact information. So those that are viewing the presentation have questions that something that may not be clear, or you'd like more information on a topic or on a specific slide of some sort, you can either send me an email here. It's mbrascoop@gmail.com, or you have my phone number here, 819-449-7751. And it would be a pleasure for me to answer your questions at that point. Also, for different communities who are thinking about implementing a project to measure the radon in the homes in their community. I'm a First Nation member myself from Kitigan-Zibi. I've been involved with different communities, either in testing projects or in doing corrective action, correcting radon problems in different communities. So we do have a lot of experience helping communities. So if there's something that we could help you with in setting up a project for your community, by all means, just give me a call or send me an email, and we'll provide you with a lot of information at that point.